This is a thing that it's up on GitHub. There's also a blog post on RStudio's blog about this. Joe Rickard asked me to blog about something. So I'm Bryan Lewis. A long time ago, I used to work in finance, and this is kind of an unsupervised learning problem out of finance that's kind of cool. So these guys have been talking in the last, about neural networks and machine learning, and there are a lot of people that do unsupervised things in machine learning, but it hasn't come up much in these talks, so I thought it's kind of interesting. Unsupervised problems are basically just given a blob of data, and you want to learn something about the data, those data, whatever it is. So you don't have labels in particular. And so for this simple little problem, we use equities data from the stock market. Let's see, how do I do that? Yeah, there we go. Oh, that's really small. That's too small. Okay. Is that legible to you or not? Let me make this over. Can people read? Is that visible?
I can read it.
Okay. So I'm going to skip. So this is I'm just going to run some live stuff. So this is up on the web, on that web page and on the blog post from RStudio. But what we're going to do is just download a bunch of stock prices from the internet. I'm not going to do that. I did it right before this talk. And I have this variable named prices. And this is the code that I used to do it. I used a package by Josh Ulrich and Jeff Ryan called QuantMod. I know there are newer packages that do this kind of thing too. But what I did though is I had a curated list of the current, I went on the internet and I got the current S&P 100 largest stocks. So that's the S&P 100 as of recently. And I just downloaded their equities data for the last several years from 2012, June of 2012. And I picked that date because that was after Facebook was listed and I wanted to include Facebook in there. So what I did was I got daily adjusted closing price data. So just the daily data. It's not that much data for all those stocks. And we can look at one of them. And then I just put them in a matrix. So we have a matrix where the rows are the days and the columns are the stocks, stock symbols. And after cleaning them up, some of them had missing data due to mergers and acquisitions or being delisted, and I removed those. So we ended up with just 96. So it's a matrix with 96 columns. So here's one of the columns. This is Apple's stock price over the last from 2012 to to today. To yesterday. Sorry. So yeah, I wish I had bought Apple stock in 2013, but yeah, it's gone up a lot actually. So that's what every column has a price series that looks like that. So so that's our raw data. That's one of the columns of the matrix, the daily price data, and it only takes a few seconds to get all of that off the internet and get to this point. And so the question is like, what can we learn about all these 96 stocks? Are there patterns in them? Are there relationships between them? It's kind of an open-ended, unsupervised question, and that's what we'll explore. So in the online blog post, there's a lot of references, and one of the things we're going to do is instead of looking at those price data, we'll look at the logarithm of the return data. And return just means assuming the first price that we see there is 1, what's the ratio of the prices? So return data is always a non-negative, in fact a non-zero number. It's the ratio of the current price to the starting price. And then we take the logarithm of that. And I'll do that. So there's a reference in the blog post from Pat Burns. Pat Burns, you should know you guys know. Who doesn't know who Pat Burns is? Do you all know who Pat Burns is? You should look him up. He's an important figure in the world of S and R. He wrote My favorite R book, the R Inferno. Everybody should read this book. It's a wonderful book. He wrote S Poetry, which is a book about R and S earlier before that. And he wrote a general book about programming called The Tao of Programming. All of those books are worth reading, actually. He's a great guy. He worked a lot in the old days on S and S+, the precursors to R, largely. And so Pat works in finance, like I did, for many easy to understand statistical reasons that I don't want to get into the details, prices may not have a nice distribution, but the logarithm of the returns in the long run are going to be approximately normally distributed. And you know, Nassim Taleb and many other economists will say that's not always true, and indeed they're right. But those events where that's not always true are interesting events. And that, oh, you know, I forgot to record. I'm sorry. I'll start recording now. There. Sorry about that. I'm recording now. Sorry. Yeah. So we can look at that. So here's a plot of here's a QQ plot. So we're plotting those prices that we were just looking at against, no, these are the prices for Lowe's, not for Apple, but just some stock, right? So this is a plot of their prices against a theoretical, you know, against what a normal distribution would look like, right? So if they were all on that slanted line, they would be normally distributed. Obviously, they're not on that line at all here, so they're really not at all normally distributed. But if we take the logarithm of the returns for that stock and do this QQ norm plot, there are tails, right, where they're not normal. They kind of deviate from normality, but the bulk of them really do fall right on that line. And this is true for all the stocks. So even if you don't buy into the theoretical justification for these data, you know, you can empirically just look at them, right? There's only 96 stocks. And why did that gives us data that we can work with now because we have a distribution. And so let's think about relationships between these stocks, between their prices or their log returns. And the most simple relationship you could think of is correlation. For example, right? I mean, are stocks correlated with each other? Are some of them correlated with others? You know, and that's kind of an interesting question. It turns out that that's a question that's fraught with a difficulty because there are, you know, even though two stocks may superficially look like they're correlated with each other in terms of price or returns, there could be all kinds of latent factors underneath that are making them look correlated, and then they're really not at all correlated. And how do you kind of tease that out? And there's this guy at Harvard, or he used to be at Harvard, called Tyler Vigen. He has this website where he's got a whole book of that's called spurious correlation, when that occurs, when you have two things that look like they're correlated, but in fact they're not. And he's got all these great he's got a whole book of this stuff. It's hilarious. So here's the divorce rate in Maine, plotted against the per capita consumption of margarine. And it's like an R squared of, it's hard to see, but it's like R squared of like 99.989. It's pretty awesome, right? You know, age of Miss America correlates very well with the murder by steam, hot vapor, and hot vapors and hot objects, right? So you really have to watch, and this is true in stocks as well. In fact, this concept of spurious correlation came out of economics, and some guys won a Nobel Prize for thinking about this problem amazingly, right? And those Nobel Prize winners, which I talk about a little bit in that blog post, invented a very nice, sophisticated method called co-integration to deal with that, but it's a little complicated, so we're going to stick with something simpler. And a simpler approach is this thing called partial correlation. And partial correlation is the kind of, on normally distributed data, all partial correlation it's the correlation of two things holding the others, accounting for all the other things. So we've got 96 stocks here, and we're going to look at two of them and look at what their correlation is keeping in mind that they're both in a set of 96 other things. You're going to try and remove the influence of these other 96 other factors and just look at those two alone. And the Wikipedia page on partial correlation is actually really one of the better, it's a really nicely written page, and there are other nice references to it. But so one of the reasons for me going into this log returns allows us to use this simple technique called partial correlation. And partial correlation is really just the inverse of the correlation matrix at the end of the day. So I just did use the core function in R to get a correlation matrix of all of our log return prices. This matrix, let's see how big it is. It's not that big. So we have 96 stocks and 1,400 days of data. It's a 96 by 1,400 matrix. And the correlation matrix looks like this. Down the diagonal, that's a particular stock correlated with itself, and those are all 1. They're perfectly correlated with each other. And then this heat map is showing on some color scale more or less correlation. It's a pretty noisy looking thing. And then let's look at partial correlation, which is really just the inverse of that. And it's actually a scaled inverse. So I just took the inverse and I scaled it. And that's a smoother looking matrix, but it's going to turn out to not do so well. So how might one interpret a correlation or a partial correlation matrix? And there's this really neat, there are many ways, right? You could just look at each number, right? Every entry, the ij entry of that matrix is the correlation or partial correlation of stock I and stock j. So you could just look at those numbers. But kind of a cooler technique is something called spectral methods, where you think of that matrix of correlations as an adjacency matrix of a network. So we're using, and then once we get this into network theory, we can use all of these tools of graph theory that are used for social networks and all these other things. And it's a very rich set of technology that we have available. And if you read the elements of statistical learning, those types of methods are called spectral clustering methods specifically, and there's a bunch of them. We'll just do a very simple one. We're going to throw a threshold on this correlation matrix and just look at highly correlated pairs of stocks. That's the threshold. I just picked it out of thin air, 0.9. We'll look at only stocks that have higher than 0.9 partial correlation with each other, so highly correlated things. And we'll treat those as connected vertices in a graph. And then, and that's it. So we can make a graph out of that with the iGraph package. That's that graph. The Q is just a thresholded version of that matrix. If I plot it, it's going to look very sparse, right? There are dots in there somewhere, but I'm not seeing them. So iGraph has this graph adjacency that takes a matrix and returns a graph for you, a network object. And then there are tons of clustering algorithms in the iGraph package. I'm going to use one called Cluster Louvain. And this is just a bunch of plotting stuff. And then we're going to plot this graph. And we get this kind of hairball. It doesn't look very useful, right? So these are our 96 stocks. And the colors are the clusters that iGraph tried to determine, but there's nothing makes much sense here. It's just a big hairball of stuff. It basically is like what we started with. It's not that interesting. And the reason for that is because if you read the references in that blog post, there were these guys in Switzerland, Ledouat and Wolf, who had a very influential paper about 10 years ago called Honey, I Shrunk the Covariance Matrix. They're economists, but it's kind of a math paper. And it's found use in biology and all kinds of other fields. And their observation was that these partial correlation problems, you're inverting a matrix. And our measurements of stocks are noisy, right? It's just a bunch of people trading and there's very noisy measurements. They're not perfectly normally distributed. We expect these things to be kind of off. And whenever you divide by something that's got noise in it, you can potentially amplify the noise and turn it into kind of garbage, right? So imagine like you're dividing something by a tiny number like 0.01. Well, that means you're multiplying it by 100. So if there's any noise, that noise is going to be amplified by 100 times. And so that's a real problem that occurs in all kinds of situations, including this one. And the solution to that is regularization. And the whole point of regularization is to just minimize the influence of things like noise or other bad behavior on the solution of a problem. And we can do that in the context of this correlation matrix problem by looking at the eigenvalues of the matrix. So here's a plot of the correlation matrix eigenvalues. And the interesting observation is that they drop off really fast. So it's got 96 eigenvalues, but really only the first 5 or 10 are large, and the rest are really small. And this is a proxy, actually very directly, for the amount of information in the matrix. And so one approach to regularizing this problem is to just cut off all the stuff associated with those tiny eigenvalues. And we can do that really easily. And when we do that, we get a really interesting looking precision matrix. And if we do the same plot of that using the graphing and the same threshold, well, now we get really interesting clusters out of our data that are, and again, we didn't put any assumptions on these data at all, other than we did a log of the returns instead of the prices. But these clusters are pretty remarkable. So let's see, let's find a cluster. So this kind of orange cluster here, those are all media companies, I think. Fox, Disney, what's TWX? I don't know some of these, right? But
Time Warner.
Oh, Time Warner, okay. And then if we look at this kind of cyan, there's a tech group here in cyan. We have Oracle, Cisco, Qualcomm, Microsoft, Apple, Texas Instruments, Verizon. Over here, there's some industrial companies, Caterpillar, 3M, General Motors. Some consumer product stuff, Nike, CVS, the Walgreens, Costco, Home Depot, Lowe's. Interestingly, where's Google? Let's see.
Google, Amazon, Starbucks in that blue.
In the blue, right? Is it here?
Yeah.
Oh yeah, there's Google. So Google and Amazon are kind of not with the other tech companies. They're over here with like Visa and MasterCard. And Facebook's in there too, right? So the prices of those stocks are much more highly correlated to kind of consumer spending than to technology, which makes sense because they're not really technology companies, those are advertising companies, right? And again, we didn't, there was no assumptions made on these data, right? We just threw a blob of data and did some correlations followed by some regularization, and you get these really intricate, interesting patterns. And the interesting thing is that now these patterns were developed over many years, but like a trader might look at this and say, well, look at this dynamically, right? And if we've got these groups that we kind of expect things to be in, and again, these groups are self-discovered by, or self-labeled, and then when something moves out of whack, that might be a trading opportunity, for example, because you might expect it to eventually move back into its group, right? That would be kind of a statistical arbitrage method, for example. But so anyway, that's it. I just wanted to show you. I'll put that link back up. I think that's the right link. Yeah. So that's an example of unsupervised learning in quantitative finance, and using all our tools. So there you go. Thanks. Shut that off. How do you stop FFmpeg from going? just hit Control C. I think it'll stop it, yeah.
I was gonna say, I can stop it gracefully. I don't know.
It looks like it crashed, actually.
Yeah, looks like you got a question over there too, Bryan.
Oh, I'm sorry. Yeah, just talk. Yeah.
How does the matrix factorization method that you used to do the clustering, how does that compare to like a t-SNE?
Don't get me started on t-SNE. So, so t-SNE is stochastic neighborhood embedding, and it's kind of all the rage these days. So it's different. So really, t-SNE is closer to kernel methods. The closest thing along these lines to something like TC would be to do a kernel principal components. So principal components on a matrix whose entries are transformed by a kernel function, whatever that means. It's something like an exponential function, for example. And those methods so t-SNE has found application in, the difference between t-SNE is that it's scale aware, right? So the cool thing about the t-SNE idea is that you can look for similarities at many different kind of scales of data. And if it's the same across a bunch of different scales, by scale I mean these parameters of these kernel functions, then you can deduce that maybe there's really a strong cluster association there with those data points. So it is a very interesting method. The problem I have with t-SNE is not the method so much as that it's unbelievably computationally expensive, and I seldom see it being, I mean, it's often for very high dimensional, these are low dimensional data. There were 96 columns, right? TC is never going to beat something simple like kernel PCA for these data. Now, if you had 1 million columns, 1 million variables instead of 96, then t-SNE might be interesting. But the problem with t-SNE in that context is that it's really computationally expensive, right? So I don't know, like I find it kind of not the best method in general. I mean, people love it, but it's more of an academic method, I think, than a practical one for many problems, for finding groups and patterns in data, in my humble opinion. But it is an interesting method, and there are two t-SNE packages that implement this method in R, actually. So you can look at them. But don't use their examples, because their examples are iris, and they aren't. Actually, it's hilarious. Like if you go into both t-SNE packages, they give you an example of clustering iris, and it's outperformed by principal components in both packages, right? So just regular principal components, not even kernel principal components. So it's not the best advertisement for that method. But t-SNE is potentially interesting for very high dimensional data sets. The other issue with t-SNE is that the embedding is only really, I think it's really just a two-dimensional embedding. They never have higher dimensional embeddings. The cool, pardon me, the cool thing about, now here we were just doing correlation, but you could imagine a kernel method on these correlation data. You could think of correlation as a distance metric, and the cool thing about using a spectral method is that the graph gives you a tangible representation of arbitrarily high dimensional data, right? We just put an edge between two things that are similar to each other, and it doesn't matter if those vertices, like when I say things, I mean a thing like General Electric. So there's an edge between General Electric and Verizon. In this example, each one of those data points are living in a 10-dimensional space, because I used 10 eigenvalues, right? So those are 10-dimensional data points that are similar enough in whatever space that is, by this correlation measure, that I put a line between them, an edge. And so what I like about spectral methods in general is that, you can't visualize when people do like principal components, you can plot a 2D PCA or a 3D PCA in 3D, but when you get to 4D, it starts to get a little dodgy, right? But if you look at it everything in terms of a graph, you can always put edges between things and visualize a graph very easily, right? So it's, I like the spectral methods just from the standpoint of, they give you nice visualizations that are easy to interpret, right? But that's just, yeah, so that's a plug for spectral when I say spectral, I mean graph network spectral methods, actually. But I don't mean to unfairly bash t-SNE. It's a one-sided thing. So there are some applications where t-SNE is very good, I think, especially in higher dimensional settings. Sorry, that was kind of a long-winded answer. Yeah.
Do we need to choose the parameter before we apply the partial correlation?
Yeah, so that I picked out of thin air this parameter 0.9, right? And there's two parameters I picked out, right? The threshold for similarity was 0.9, and then the other parameter was how many what dimension eigenspace to pick, right? How many eigenvalues to, and in this example, I just picked them, right? So in both cases, you can make that more systematic. Now in the eigenvalue case, you saw that curve, they drop down really fast, right? So you can kind of, one approach that people do that's heuristic is you eyeball that curve, right? And say, well, look, after this point, basically nothing is happening, right? But there are other more systematic approaches. That's called regularization parameter selection. And there's a whole literature about that. And then for the thing that on the spectral method, the 0.9 the threshold of what's close and what's not, where to put an edge, you could if you go to that address there, there's actually a slider on these graphs where you can see how that, obviously the lower your threshold gets, the more connected the graph becomes, right? And so you can either manually futz with that parameter, or you could use like a cross-validation approach to pick a parameter that gives you a balance between the cluster sizes, right? For example, like you would do with k-means or anything. But it's always an issue with kind of unsupervised techniques, like how do you pick the clusters? In this particular example, like you could just look at it, right? Like these make sense. You know what I mean? It's kind of you have a kind of a human feedback loop with this stuff. But yeah.
If you add more parameter, so the number of clusters will be increased, right? So you'll get more clusters.
Yeah, well, what happens is like the graph gets more connected, so you actually start to get less clusters, right? Because you get like greater connectivity, right, between things. Like as the parameter gets, like if we set, it's a correlation number, right? So it's a number, think of it between like -1 and 1, right? So like from anti-correlation to correlation, right? So like if you pick a correlation of 1, then we're gonna have 96 points here, no edges connected, because they're all correlated to each other with the value of 1, but nobody else, right? Unless there happen to be two stocks that were identical, right? And there are on here, actually, there's 2 Google stocks listed, right? There's Google and Google, it always confuses me because there actually are 2 Google, there's Google, see that? There's 2 Googles. One's Goog and one's with an L, right? And they're both Google, and they're almost perfectly correlated with each other. There's some, I don't know what the difference is, but they're both on the stock exchange. It's kind of weird. But then in the other extreme, if you go down to like a correlation of 0, then then there's a line between every point, right? And it's just a big hairball again, right? So you have to kind of find a balance between within group and between group distance or correlation here, just like you would with k-means or any other clustering algorithm for the most part. So you could do it automatically with cross-validation on some metric like that, or you could, in my case, I just put a slider on there and eyeball them, here. Maybe not the most satisfying answer, but, and then obviously if we picked a different, I picked correlation and an eigenvalue decomposition, but you could do principal components or t-SNE and come up with something similar, and there would be a different family of parameters associated with those methods, of course. Like if it was a kernel method, you'd have the parameter for the kernel, for example, in addition to this other stuff. This is kind of the simplest case. But it's pretty cool, though. Like, I'm always shocked when I do this. I actually just recomputed it today, and again, it's always amazing to see this kind of pattern emerge from just a bunch of numbers. That makes sense. By the way, this graph visualization works with iGraph, and it's a package I wrote that's on CRAN that plots networks like that. It's called 3JS. So check that out too.
How does this method scale with, like, if you had 10,000 tickers, or if you had minute per minute data?
Yeah, so the code I have well, the minute per minute data is not a problem because that's just more rows. You'd still end up with a 96 by 96 matrix here, right? So at the end of the day, if you've got, I mean, there's about 10,000 equities on the stock market. So at most, you're going to have a 10,000 by 10,000 matrix, even if you did the correlations, right? And that is something that fits on even my crappy Chromebook. Now, if you were in some other field like genomics, where you had, potentially millions of variables, that's a different story. And then you'd have to. So then there are things you can do. If you're doing correlation, there's a paper that Jim Baglama at University of Rhode Island and I wrote that is not yet published. It's on archive, called T-Core, which is a very efficient thresholded correlation algorithm that only produces the pairs above a given threshold. So you could create a very sparse representation of those data without computing them all, right? Very efficiently. So if you were into these super large scale, and we did that on things like Chromebooks with 400,000 variable data sets, and you can do that, right? So for scaling out wide data in this kind of problem, you have to, and basically all that paper does is a trick like using those eigenvalues, right? You're projecting into some lower dimensional space in a clever way that gives you back just the thresholded stuff that you're interested in. So it's no big deal, right? But we don't know where we're going to send that paper yet, but it's up on archive. If you go to my website, it's there somewhere in the links. Okay, I'm going to go have beer at Melt, I guess. So thanks.